guys, what's up? This is part 2 of digital electronics and computer architecture. In this video we'll be going over Boolean algebra and a bit more about logic gates. So let's just go in. So yesterday we learned about the AND gate. We know the AND gate, we know the OR gate, we know the NOT gate. Okay? We also know the XOR gate, or I'll put on the side. We know that there's a NAND. We know that there's a NOR. We know that there's a buffer. We know that there's a XNOR. So if you don't know these, you should watch the first video, get a good understanding of what these gates are and the truth tables that they provide. Okay, so let's go over a bit more about logic gates. So let's take a NOT gate. Okay, and we feed that into another NOT gate. Okay, and let's say I have a 0 here. So we could conclude that at this point x, we're gonna get a 1 because it's going through a NOT gate. Then we could conclude at this point y, we're gonna get another 0 because it flips the 1 that's here, and you get a 0 here. Okay, let's try something else. Let's do the same thing. But we put a 1 here. So we're going to get a 0 here because it flips it. And then it's going to flip the 0 and we're going to get a 1. So what could we conclude? We could conclude that A, we call this input A. So these two are just the same pictures. We could conclude that A not A is equal to A. Right? So if you say I'm not hungry, right? You're not hungry. So you're canceling out the nots and it creates a positive again. So this is called the double inversion law, right? So if you invert something 2 times, you're going to come back to the original state. That's what the double inversion law says. Okay, that's pretty good. Okay, now I want to go over chaining AND gates and OR gates. So I'm going to chain them, and we can make big AND gates and we can make big OR gates. Okay, and this will translate into the NORs and the NANDs. So let's just draw an AND gate here, an AND gate here, and let's connect the output of the first AND gate. So I'm going to label this guy as 1. I'm going to label this guy as 2. So the output of the first AND gate is going into the input of the second AND gate. Now we connect one long input coming in here, and we get 2 inputs here. I'm going to label this A, I'm going to label this B, and I'm going to label this C. Okay, let's think about this logically. Remember the tap analogy, right? We're going to have to turn taps, and we want to see what comes on the output. So let's just draw a truth table. So we get A, we get B, we get C, we get X. Okay. It's gonna be big because there's 3, so we have to draw all the combinations of the 3 taps. So we have all of them are off. We have C is only on. We have B is only on. We have B and C are on. We have just A is on. We have A and C. We have A and B, and we have all of them on at the same time. These are all the different combinations. There's 8 of them. Okay. What does the logic tell us for just A and B? Forget the whole C column. The whole C column, just forget about it. Don't even look at the C column right now. Just look at A and B. A and B are only going to be true if A and, because these are AND gates, remember, if A and B are true, then the output's going to be true. So we could only continue to look at these inputs, right? We know that anything out of here is going to be a 0 because A and B, they're not 1s in any of these combinations other than the ones I put the parentheses around. So we know that all these we could just fill with 0s automatically. So 1, 2, 3, so there's 6. Okay, now we could pretend we're only looking at these 2 conditions and we get a 1 here. Just these 2 conditions produce the 1 here. But for this AND gate to turn on, C needs to be high. Okay, and we have 2 possibilities in the C column now. Okay, so we could conclude that since this input is a 0, this AND gate won't ever let electricity or water, whatever you want to think about, go through. So we're going to conclude that this is a 0, and only if A and B and C are 1, we get the 1 at the bottom. So this is how you chain AND gates. Now this could go on for infinite amount of chaining. Okay, you're going to get a gate delay, but who cares about timing right now? We're just learning logic. Okay? So you could chain these as much as you want. Make a 75 input AND gate, a 9054 input AND gate, whatever you want. And it's going to follow the logic that if all of them are on, then the output will be on. Okay, cool. Okay, let's do something for the OR gate. Let's do the OR gate. So we're going to do the OR chain. Okay, so let's draw an OR gate here. Let's draw the OR gate here. And if this is a little bit confusing for you, I recommend watching the first video again just to get a refresher. So we get our output X, we get A, we get B, we get C. So let's draw the truth table. So we get A, we get B, we get C, and we get X. And we draw out the combinations. So let's do this. 0, 1. And by the way, the combinations is just binary numbers, and I'm going to be explaining the binary number system after we cover all of Boolean algebra. This is called Boolean algebra. Okay, and I'm going to introduce the mathematical Boolean algebra just after this. Okay, so we have OR logic now. Okay, we label this guy as 1, we label this guy as 2. Now for A and B, for a logic gate 1 to get a, we want a 1 on this output, right? So for logic gate A and B, how do we get a 1 on this output? There's got to be at least 1 1 on the A and B. So okay, these guys, there's no 1s at all, but all of these in parentheses, they're always having a 1 somewhere, right? So we could conclude that there's going to be a 1 here, a 1 here, we get a 1 here, a 1 here, a 1 here, and a 1 here. Because this is OR logic. Any of them could be on and it'll activate this gate. We're only looking at A and B, forget this whole column. I'm only interested in A and B. And in these two columns, I mean in all of these rows that I label with the parentheses, there's at least 1 1 somewhere. Okay? Now let's deal with the C. Now C is coming into an OR gate, and we have the previous condition, so our condition is only looking at these now. It doesn't care about the other ones. Okay? And and we want to find the first and the second column entries. The rows for the entries. Okay, we know that if none of them are on, none of the taps are going to be open, and OR logic won't let anything go through. So there's going to be a 0 here. But we have C, and if a 1 is here, and pretend we're looking at this column, so A and B are 0, so we get 0s here, nothing goes through. But we have OR logic. So we have C or the previous condition, and this will still give us a 1. And this is how you could chain OR gates together. You could chain these together. Okay. Pretty cool. So for the chained AND gates, we just draw them just as a big gate with like multiple inputs coming in. Okay? And we could have the NAND version. So you could invert it, and it's going to be an OR gate. Remember, in the last video I explained De Morgan's theorem. This is the same thing as just a big OR gate. That's thinking of zeros as ones and ones as zeros. This is the same thing. And you get the multiple inputs coming in. Okay, cool. Now we have the mega OR gate that I just explained in before I erased. And you could have multiple inputs come in. Okay? And you could have the NOR version of that. Okay? And then this, so this is an AND. Wait, let me just write this down. This is an AND. This is a NOR. Okay? And this is also a NOR. So we get a big AND gate. And you just draw the NOR. And you have to invert the inputs. Okay, so this is a big NOR gate. Okay? This is pretty cool. Okay. Now I think we should go over some of the laws. So we want to go over the AND laws and the OR laws. So let me just pull up my sheet just so I don't make any mistakes. So first, we're going to go over the identity law. The identity law just says we get an AND gate. Okay, we have an input here and an input here. We tie a 1, just a solid 1. This one's not changing, and then we have an input A. What the AND law says is that the output is going to be A. Okay, let's draw the truth table for this. Why? We only have one input, A. It can only be a 0 or 1. We have output X. Okay, now since this is tied on a 1, right? Whatever is on the A, so if there's a 0, there's going to be AND logic that says, okay, A, the first input and the second input both need to be a 1, but there's a 0 on A, so we're going to get the 0. So the 0 from here is transferred automatically. Okay, but if there's a 1, the AND logic is going to tell us that, okay, the first input and the second input are true. So the A is going to be transferred. And we could conclude that just A is transferred if one of the inputs is always tied high. So this is the same thing as just having a straight up wire. Nothing different. Okay, this is called the identity law. Okay, now let's try and put a 0 instead of the 1. So we get the AND gate again, but we put the 0 here and A. Now let's draw the truth table. And okay, but this is pretty simple because at all points in time, at least one of the inputs are going to have a 0. So there's never ever going to be a 1 because they can never both be 1 at the same time because one of them is always tied to 0. This is called the Null Law. Okay. Now let's go over the Idempotent Law. The Idempotent Law just says if I take an AND gate and tie the two inputs together, right, and I label this guy as A, the output is still always going to be A. Now let's draw the truth table. So we have A and we have X. And we have 0, 1. Okay, if we have a 0 in here, both inputs are going to be 0, right? It's going to give us a 0 because AND says A and B inputs need to be a 1, then you get the 1 on the output. Now if A is a 1, it's tied to both inputs, so both input gets the 1. So this is transferring the A from here automatically to here. This is the same thing as just having a straight up wire. Okay, let's go to the inverse law. So let's draw an AND gate with this. With the output X, we have an input here, but chaining off this input we put a NOT gate, and we end it into here. This, and let me just draw this. This is the exact same thing, nothing different in what I drew. These are the exact same. You could just put a circle on the input to represent that it's inverted. Okay, what this tells us, so these are inputs A, and these are X. What this tells us is that, okay, let's put a 0 here first. Okay, so we're putting a 0 here. And on the inverted side, we're going to get the 1. Okay, what this tells us is that there's going to be a 0 somewhere. So the AND is, okay, let's just draw the truth table, just to simplify this, so we get 0, 1. The AND is going to tell us, okay, there's at least one 0, so we're going to automatically get the 0. Okay, let's pretend I put a 1 here. So a 1 is coming in, so we get a 1 here. This guy flips it, so we get the 0. Okay, so this is telling us that at any point in time, no matter what you do, you're going to get at least one 0 on the inputs. This is called the inverse law. Okay, so there's 2 more laws that we need to go over. And we get the easiest of the laws, which is called Commutative Law. It just says that, that's all it says. You label this guy as A, you label this guy as B. This is the same thing. I'm just labeling this guy as B and this guy as A. These are equivalent, nothing different. You're just changing the input names. Okay. Now there's something called the Associative Law. It's kind of similar, but let's say we have an AND gate here, and we did the chaining thing. And I labeled this guy as A, B, C. This is the same thing as just doing this. Labeling this guy as C, let's say I label this guy as A, and label this guy as B. You could label them whatever you want. It's still going to be an AND gate, a big AND gate. Okay, cool. So these are all the laws of the ANDs. All the AND laws. Okay, cool. Let's go over the OR laws now. So the OR laws. So this is the identity law for the OR gate. So we draw the OR gate. We get output X. Now let's tie one of these inputs to 0, and we have A. Okay, let's draw the truth table. Okay, so this guy's always 0. And okay, if A is a 0, we're going to get a 0, because none of them are going to be on. This is OR logic, so it's choosing OR, so we get a 0. And if A is on, then at least one of them are going to be on, so we get the output here. So this is called the identity law. So it just tells us that the output is always going to be A. Okay, let's go over the null law. Okay, so we draw the OR gate again. We tie one input to 1, one input to A. Okay, let's draw the truth table for this. And we get the output X. Okay, at least one of them are always going to be a 1. So this is pretty trivial. So we have the combinations. There's always going to be 1 because I tied this one high at all times. So the output will always be 1. Okay, now let's go over the idempotent law of the OR gate. Okay, so if we take an OR gate, tie the two inputs together, label it as A, and this guy is X. So we have A and we have X, and these are the two combinations. Okay, if it was 0, both inputs are 0, so that's just going to give us a 0 because the two inputs, none of them are ever going to be on. Now if we have a 1, both inputs are going to be on, so you get a 1 here because the input 1 is on and the input 2 are on both at the same time. And this is following the OR logic, so we get a 1. So this is called the idempotent law. Okay, next we get the inverse law. Okay, inverse law, let's draw this. Okay, I'm going to put an inverter chaining off here. It's going to go into here. You have A, you have X. So let's draw the truth table. Okay, let's pretend we put a 0 here. We have a 0 here. Okay, the 0 is also come through, and then it gets inverted, so we get the 1. At least one of them are on, right? So if you put a 0, we get a 1, right? Now let's pretend I put a 1 here. We don't even need to think about this input, but it's going to be the inverted version. But at least one of them are on again. So this is the inverse law. Okay, it says that if you invert one of the inputs and you tie it to the other, you're always going to get a 1. Because at least at all times, you're going to get a 1 on the output. Okay, and then we have the commutative law, which is very easy. It's just saying A, B. This is the same thing as calling it B, A. Pretty simple. Okay, we have the commutative law also. Pretty simple, but I'm just going to go over it. So we pretend we have the chain of the ORs. We have A, we have B, we have C. This is the same thing as just labeling them any way that I choose. So I'm going to go A, B, C. This is the same thing, nothing different. Okay, cool. So we went over the OR laws, we went over the AND laws, we went over chaining ORs, we went over chaining ANDs, and we also went over the double inversion law. Okay, cool. Now let's jump into the XOR area. Okay, so let me change the color. So let's draw an XOR gate and the truth table with it, just as a refresher, because we didn't touch upon it at any time in this video. So we have the output X, we have A, and we have B. Let's draw its truth table right on the side. So we have A, we have B, we have X, and these are the combinations. And remember, the XOR is exclusively OR, so it's an OR gate that's exclusive. So if both of them are on, it's not going to allow the one to go through. Okay. Now what if I wanted to represent this XOR gate with only using AND gates, inverters, and OR gates? Okay, we could do that. We could do that. So I know that there's some sort of OR logic, so we're going to make some sort of equivalence. So 3 lines means equivalence. So I'm going to start off with the OR gate. Okay. And we have 2 inputs coming in. Okay, so far the truth table for this is telling me that, let me just draw the truth table for this so far. So we have A, B, X, 0, 0, 0, 1, 1, 0, 1, 1. So this is the truth table for the OR gate. But I want to make a circuit that converts this into the XOR. So we want to go from this, and we want our truth table to end up being this. Okay, how do we do this? Now, do you remember De Morgan's theorem? Okay? Do you remember De Morgan's theorem? All it says is that the NAND gate could be thought of as an OR gate that's looking for zeros, right? We want to cancel off this one condition. Like, we want to just inject a 0 when it detects that a 1, 1 comes. Okay? How do we do this? This is where we add a NAND gate. Okay? We add a NAND gate. Okay? Because the NAND gate is just looking for the inverted zeros. So let's draw this. So we put a NAND gate. And we chain it like this. Okay? That's cool. But we want to add these two conditions together. So we get the OR condition and the condition that's injecting a 0 for this one part. And this is an XOR gate. Now let's make sure that this is an XOR gate. Let's really test it and put it through all its conditions. So we have A, we have B, we have the output X. Okay, let's do 0, 0, 0, 1, 1, 0, 1, 1. Okay, let's start with the first column, 0, 0. So let's put in the 0, 0. So we get a 0 here, a 0 here, a 0 here, and a 0 there. Okay, this gives us a 0 here. So automatically we're going to get a 0 there because we don't even need to see this condition, right? We don't need to see this condition. This is an AND gate, so we automatically get a 0. Okay, let's do the next condition. So let's erase all this, 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 and this. Okay, let's just get rid of that. And let's go to the next condition where A is a 0 and B is a 1. So A is a 0, B is a 1. We get a 1 here and a 0 there. We automatically get a 1 coming in like that. Okay? But if we have a 0, 1, we're also going to get a 1. Just check the NAND truth table. The NAND is an OR gate that's looking for a 0. So this is an OR gate that's treating the zeros as 1. So we're at least getting a 1 coming in. And this satisfies the condition. So we get two ANDs. I mean, the AND is seeing that there's two 1s on the input, so we get a 1 on the output. Okay, pretty cool. Okay, let's do the other condition, where A is a 1, and B is a 0. Okay, so the 1 goes here, and the 0 is there. Now this is basically the same thing, it's just flipped. So this is sort of like the associative or commutative law. Right, so we get the 1 here, because it's an OR gate. It sees at least one of the 1s. And this is an OR gate that's looking for a 0. Right? And we have at least 1, 0. So we get a 1 on the output. This also satisfies the condition. Okay. Now let's do the final entry. The very bottom entry where A is a 0 and B is a 0. Let's do that one. I mean, A is a 1 and B is a 1. So we put a 1, 1 here. At least one of them are going to be on. So we automatically know that there's a 1 coming in here. Now, the only way is to see if this is a 0. This has to be a 0 on the output. So we put a 1 here and a 1 here. Now this is an OR gate that's treating 1s as 0s. So this is technically an OR gate who's seeing 0s only because both of the inputs are 1. Okay, so this does not follow OR logic. So you get a 0 there. And bingo. This and this are the same. So I just proved to you that the XOR gate could be made using one NAND gate, one OR gate, and one AND gate. Okay? Cool. Okay, so now let's go over some laws. I just need to go over a few laws, and then we can move into Boolean math. Okay, so I'm going to tell you something called the absorption law. So I'm going to draw out a circuit. We have an OR gate here. We have an AND gate here. Okay. What the absorption law tells us is that we need to label. Okay, actually I drew this wrong. So this guy is coming in and chaining. So we have this as A, this is B. So this point is also A, and we're going to call it this point A or B. We're going to go over Boolean algebra later, but what does this truth table tell us? Well, I don't think we need to draw a truth table. If we're using English language, we know that this is an OR gate, and this is an AND gate, right? Let's think about this in English, okay? A or B, they could come in, but the A is also tied into the AND, right? So all this is telling us, okay, if at least A is on right now, forget B, just forget B, don't even care about B. Pretend A is on, we get a 1 here, and that 1 is also transferred here. This condition is true. If A is a 0, okay, the 0 comes here, but the 0 comes here, B could be whatever, so it doesn't even matter, so we're just going to put like X, because it could be either a 0 or a 1, right? It doesn't even matter, right? A is a 0, the B is coming in, it doesn't even matter. But if this is a 0, this 0 is also going to get transferred here. So this is AND logic, right? There's going to be a 0, so this is always going to produce the 0. So what we could conclude is that this circuit is that the output is always going to be whatever A is. This is called the absorption law. I think it's called the absorption law because we're absorbing only the A, we're forgetting about the B. And this is used in simplifying your Boolean circuit, so don't just throw these ideas out the window. This is going to come in handy when you're trying to simplify your very complicated circuit and reduce it down into as small as possible. Okay, now there's another version of this. And what if you flip that, the AND gate and the OR gate's position? So this is the second absorption law. And this guy is going to be coming like that. You label this as A, label this as B. And we label this guy, this is the chain that's coming in for the A. Okay, let's forget about B. Forget about B. Pretend A is a 0. Okay, pretend A is a 0. So we have a 0 here, and also a 0 here. Now the AND logic tells us, okay, even if at least one of them are 0, we're going to get the 0 on the output. So A was originally 0, so the 0 is automatically transferred. Okay, now what if A is a 1? So we get a 1 coming in here. Doesn't matter about the B, but at least there's going to be a 1 here coming into the OR gate. So the 1 that's coming in from A is automatically transferred, and we could conclude that the output is always going to be whatever A is. The output is always going to be whatever A is. This is the second absorption law. Okay, pretty cool. So we're going to continue with the distributive law. So what the distributive law just says is that we have an AND gate here, we have an OR gate here, we tie the output to this input, and we have 3 inputs in total. We have A, B, and we have C, and we have output X. This is the same thing as having 2 OR gates, both of them feeding it into an AND. Okay, we get C here, we get A, we get B, but A is tied to this input. These two circuits are the exact same. This is called the distributive law. Okay? Now there's a second distributive law, and we're going to be flipping the roles of the OR and the AND. That's what the second distributive law says. And don't just forget about these, because these are really important. So you could pause the video and just make a note of these. So I'm just trying to introduce you to these laws because they're really important for simplifying Boolean circuits. So we get B here, we get C here, and we get A there, we get the output, and we get X. This is the same thing as having 2 AND gates. Both of them feed into an OR gate. You get your input C, you get your input A and B, but A is tied right into the other input. These are the exact same. Now this is the distributive law. So, oh my god. Okay, so I went over all the laws. So just to go over a recap, we went over the double inversion law. We went over how to chain ANDs and ORs. We saw the NAND version of that and the NOR version of that, of having a huge AND gate, having a huge OR gate, having a huge NAND gate, having a huge NOR gate. Okay, We went over De Morgan's theorem in the other video. Extremely important. I can't stress that enough. De Morgan's theorem. You gotta think of NAND gates as OR gates that are looking for zeros, and you gotta think of NOR gates as AND gates that are looking for zeros. Okay. We went over the absorption law. There's two absorption laws. We went over the distributive law. These are the laws, and I showed you an equivalent way of creating an XOR gate using an OR gate, a NAND gate, and an AND gate. Okay, we could also do more. Okay, so this is going to be the final part of this video, and this is going to be talking about universal gates. So it turns out that you could literally simulate any circuit only using NAND. Only using NANDs, you can make any other circuit you want. Okay, and only using NORs, you could also do the same thing. So these are universal. Now, I'm going to draw out how to do each gate using NANDs right now. So if you want to use NANDs to make a NOT gate, let's make a NOT gate. So what we're going to do is we're going to have a NAND gate, two of the inputs. This is a NOT gate. Okay, let's say I want to make an AND gate. Okay, so we take a NAND gate. Okay, an AND gate is just the opposite version. So let's tie this inverter that we just created. Okay, so this is the inverter. So this is an AND gate, right? Cool. Now let's make an OR gate. Okay. Now remember that the NAND gate is just an OR gate that's looking for zeros. Okay. So let's just start off with an AND. Now let's invert the inputs with these NOTs. So let's just draw that. So we put an inverter here, and we do the same thing. This is an OR gate. Okay. Now what if I wanted to make a NAND gate? Okay, I don't need to because it's already a NAND gate. What if I want to make a NOR gate? So we just take this block. So we take this block, and we let me just chain it off of this one. So this one is going to be NOR. We're going to convert the OR gate into a NOR gate. All we do is chain another inverter here, and this becomes a NOR gate. Okay. What if I want to make an exclusive OR out of just NANDs? Let's make an exclusive OR out of just NANDs. Okay, so this one's a little bit more complicated. I'm not gonna go through the like the full truth table. You just have to accept that these are facts. You could go through the full truth table. I think it's good practice. But what you're gonna need is 4 NAND gates. Okay, then these guys feed into here. These guys feed into here. You get your output. Okay, then this guy gets split into these guys. Now these guys come in, and they chain off of here. And, okay, this is an XOR. Okay, if you want to make XNOR, you could chain. If you want to make XNOR, you could just chain the inverter, and this will be XNOR. So we put XNOR. Now, because I chained the inverter, this is the XNOR. But if I were to just delete that inverter, this is now just the XOR. There's also another way to make an XOR, and I'll make that right now. They both take 5 gates to make, so they're exactly the same in efficiency and cost if you're just looking to make logic gates only using NANDs. So let me just draw this one out. This one also takes 5. So let's draw this out. But I feel like, I don't know which one's more easy to make. I feel like they're just both a little bit complicated, a little bit. But once you start doing a lot of practice, logic gates become pretty easy. So let's chain these two. Okay, we have A, we have B. Okay, this is an inverter. Okay, this is an XNOR. Okay, cool. Now, let's do the same thing, only using NOR gates now. So we're going to use a NOR gate and create all the other logic gates just using NORs. Okay, so we want to use the NOR gate and let's try to make a NOT gate. Turns out we could do the same thing. You can make a NOT gate just like that. Now what if we want to make an AND gate? Okay, first let's make an OR gate first. Okay, so first we start off with a NOR, right? And we just chain this NOT gate and it'll become an OR, right? Because it inverts it. This is an OR gate. Now let's try to make an AND gate. Remember, a NOR gate, just a regular NOR gate, is an AND gate that's looking for zeros. This is De Morgan's theorem. So let's try to make an AND now. So let's just start off with an OR gate. Okay? And let's chain these inverted NORs right into these inputs. So these are inverters, and this is an AND gate. Okay, and what if I wanted to make a NAND gate? If I want to make a NAND gate, all I do is I chain an inverter right there, then it's an AND gate. Okay? Now if I literally just delete that inverter, then this becomes an AND. Now let's try to make the XOR, and let's try to make the XNOR. Now here's a pattern I'm going to tell you. The XNOR looks like the XOR from the NAND. So let's draw the XNOR first. So the XNOR looks just like the XOR version using NANDs. What do I mean by that? You're going to see it's that same pattern, but this is the XNOR. So I find it really cool that these patterns arise, like opposite version patterns. Right? This is what I really like about digital electronics, is the patterns that you could, the inversion patterns. So this is an XNOR. Now I could turn this into an XNOR by chaining that inverter boy to the end. So this inverts it, then it's an XOR. Okay, but what if I want to make an XOR in a different way using 5 logic gates, and it follows that same pattern that we saw with the NANDs? Okay, so we're going to be drawing. So I suggest that you scroll back in the video a little bit and go over the NANDs again, see the pattern of how I drew it, and then come back to the NOR and you'll see the pattern. They're just opposite configurations. So let's draw the XOR in a different way. Okay? Okay? Okay, these guys have to act as inverters. So you get your inputs here. So this guy's coming in, and this guy's coming in there. And they both chain it up into another NOR. Okay? And eventually, they all meet up in this final stage of NORs. This is an XOR. Now if you want to be so inefficient, you could turn this into an XNOR by just chaining off that. But I showed you before that it's possible to make. So this is now representing an XNOR because I put this there. But this uses 6. You can make the XNOR using 4, which I just showed before. So these are literally all the laws. So I just want to go over Double Inversion Law again. What if I have this inverter? What if I have this inverter? And then what if I have this inverter? This is the same thing as just having one inverter. An odd number of inverters in series is just can be simplified into an inverter. Okay, an even number of inverters. So we have an even number. Let's just draw 2 because 2 is even. No, let's go for 4. So 4 is also even. This is the same thing as just having a straight line with no components in the middle. This is just Double Inversion Law. And yeah. So this is the end of the video. Next video I'll be going over Boolean Algebra. So how could we represent this in math? Make a language that we could do algebra on, simplify some circuits. Because the goal of computer architecture is to make the most powerful machine as cheap as possible, using the least amount of gates, but also as fast as possible, as efficient as possible. So this is why I'm teaching you these different laws, because we use these laws to minimize our big complex ideas and we try to minimize it into the smallest circuit possible.